Welcome back, students. Now we will discuss another topic, that is electric potential. Okay, so now we will find out some of the important problems of problems based on the potential, electric potential. We will consider some important points now. We will discuss, and then straight away I will tell you some problems based on this concept. So we know that the electric potential at a point is defined as the negative line integral of the electric field from infinity to that point along any path. And V of R is equal to minus of integral infinity to R E dot dr. And another expression for the potential is, for potential at a point is V of R is equal to KQ by R. Okay. So another potential expressions for potentials are, or the potential, we know that is the work done for taking a unit positive charge from one point to other against the electric field. So the work done in a potential field is WAB is equal to Q into VA minus VB. So the potential difference between the points is W by Q, or VA minus VB. So next another important term is this one, electric dipole. So the expression for electric dipole, V of R theta, potential due to a dipole is QA cos theta divided by 4 pi epsilon 0 R square, and P means QA is the dipole moment, P cos theta divided by 4 pi epsilon 0 R square. So the potential of a point lying along the axial line will be P divided by 4 pi epsilon 0 R square. And for the equatorial lines, the potential of the dipole will be 0. So next we are considering, we have some n drops having charges, having some charges, and these n drops are coalesced to form a one big drop. Then the radius of the big drop, that becomes R, is equal to n raised to 1 by 3R. I hope you are remembering all these things. And Q is equal to total charge on the big drop is equal to n into the charge on each drop. And the volume of the big drop becomes n into 2 raised to n raised to 2 by 3 into the volume of the small drop. And the charge density sigma is equal to n raised to 1 by 3 into sigma small, and energy electric field is n raised to 1 by 3 into E small. Okay. So then the kinetic energy of a charged particle moving in a potential surface or potential difference surface, the kinetic energy is equal to half m v square, and that is equal to EV. EV is the applied potential. And another important element is the capacitor. So the capacitor, the expression for the capacitance is C is equal to Q by V. You are familiar with that. And the capacitance of a spherical conductor is C is equal to 4 pi epsilon 0 R. And the energy stored in a capacitor is half CV square. And if some capacitors are connected in parallel, the resultant capacitance is C1 plus C2 plus C3. Then if instead of this capacitance, suppose we have the resistor, then when the resistors are connected in parallel, the resultant resistance is 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And the capacitors connected in series, this is the expression. And for the resistors which are connected in series, resultant resistance R is equal to R1 plus R2 plus R3, etc. Okay, so now we will do the problems based on this. The electric potential V as a function of distance x is given by V is equal to 5x square plus 10x minus 9 and the value of the electric field at x is equal to 1 meter. This is the question we have to evaluate now. So it is given that the potential V is equal to 5x square plus 10x minus 9. So now you should remember an expression that will relate the electric field and the potential, and that E is equal to minus dV by dx. E is equal to minus dV by dx. So for getting the question is, we have to evaluate the electric field at x is equal to 1 meter. So the electric field E becomes dV by dx. So that is minus O dV by dx is differentiating with respect to the potential V. So that is 5 into 2x plus 10. So our V becomes minus of 10x plus 10. Okay. So we have to evaluate at x is equal to 1 meter. At x is equal to 1 meter, electric field E is equal to minus of 10 into 1, 10 plus 10. So that is minus 20 volt. So the answer is option A, minus 20 volt per meter. Second question. Two charges plus 10 microcoulomb and plus 13 microcoulomb are placed at a distance of 6 centimeter apart. Find the electric field at the center of the line joining charges. Find the electric potential at the center of the line joining charges. So we are just doing a mapping of this one. So we have two charges, one having 10 microcoulomb and another having 13 microcoulomb, and the distance between them is 6 centimeter. Find the electric potential at the center of the line joining charges. So here we have to evaluate. The point P is here and the distance, this distance is 3 and this distance is 3 because at the center. So the potential at the point P will be, we know that the point charges Q by, for point charges, the potential at a point will be KQ by R, this one, plus KQ2 by R. So this becomes K into 10 into 10 raised to minus 6 divided by 3 into 10 raised to minus 2 centimeter and meter plus 30 into 10 raised to minus 6, 30 microcoulomb into 3 into 10 raised to minus 2. Okay. So we know that for the value of K is 1 by 4 pi epsilon 0, value we can write as 9 into 10 raised to 9. Denominator same, so this becomes 40. 40 into 10 raised to minus 6 divided by okay. So this one potential Vp, we can write it as Vp is equal to 9 into 10 raised to 9 into 40 into 10 raised to minus 6 divided by 3 into 10 raised to minus 2. So the answer we are getting that 1.2 into 10 raised to 5. Okay, 3 and this 3 will cancel. So this becomes 12. So that arranging this one numerator, this power of this 10, we will get 1.2 into 10 raised 1.2 into 10 raised to 7, 1.2, because this one will move up. So this becomes 10 raised to 11. So 11 minus 6, we will get these values, 1.2 into 10 raised to 7. So the correct answer is option A. So next question. A hollow sphere of radius 1 meter is charged such that the potential on its surface is 40 volt. What will be the potential at the center of the sphere? Okay. A hollow sphere of radius 1 meter is charged such that potential on the surface is 40 meter. It is given that because of some charges, a potential is existing on its surface, that is 40 volt. What will be the potential at the center of the sphere? So it is not given that any charges are placed at the center of the sphere. So that means it is not specified that. So it is clear that there is no charges are placed inside the sphere. So the potential, since there is no charges between the surface and the center of the sphere, the potential inside will also be the same as that on the surface. So the answer is option. So the answer will be option B. So next question. What will be the work done on moving a charge of 5 microcoulomb from a point A to B via the given path? So we have to find out the work done for bringing the charge B to A. The value of the charge is 5 microcoulomb. So we know that the work done or the work required is final point to bring from A to B. Final point minus initial point, VB minus VA into Q. So Q is given that 5 microcoulomb. So that means 5 into 10 raised to minus 6 into the potential at the point. Okay, we have to bring the point A to B. Point A to B. So potential at B is 2 and the potential at A is 5. So the value is the work required to bring the charge from A to the point B is W is equal to Q into VB minus VA. So 2 minus 5 is minus 3. So the answer is minus of 5 into 3 into 10 raised to minus 6. So the answer is 15 minus of 15 into 10 raised to minus 6. So it is given that is equal to minus 1.5 into 10 raised to minus 5. So the correct answer is option C. Okay. So practice more problems based on these equations. Thank you.